I'm Bedran from the Ruhr University Bochum, and today I'm going to present our latest research on bidding down attacks and mitigations in 5G and 4G. This is a joint work with Nils Fürste, Rupprecht, and Katharina Kohls. Mobile networks today play an indispensable role in our daily lives, be it calling your loved ones or just surfing while on the go. Lately, mobile networks are getting more important for critical infrastructure as well, such as self-driving cars or automated industry. All of this comes with a high need for security. LTE, followed by 5G, introduce new security mechanisms to ensure that your connection is secure and cannot be tampered by an attacker. The question we try to answer today is if an attacker can bypass or bid down these newly introduced security features. I will explain more characteristics of bidding down in a bit. First, I want to give some quick technical background. I will keep it quick because I think you're going to see it multiple times today. So the UE, the phone, is connected to the base station via the radio channel, and the base station is connected to the core network and relays the packets and data between the core network and the UE. Important to note is that the UEs, including the basebands and also the network equipment, come from different vendors. This is important because different vendors have different implementations, and thus you can find different security vulnerabilities. I just want to give some quick introduction to two protocol layers we looked intensively into. The NAS layer manages basically the connection between the UE and the core network, and the main tasks are, for example, authentication and also activating the security on the connection between core network and UE. The RRC manages the radio connection between the base station and UE. One of its tasks is also to activate ciphering and integrity protection on the radio channel. So now I want to give a quick introduction to bidding down. We have classified bidding down into intergeneration bidding down attacks, where basically an attacker tries to downgrade the victim to an older and less secure network generation, for example 5G to 2G. Here's a funny analogy with the cars. For example, you can imagine a driver changing from a super new secure car to an old car without any safety systems. An intra-generation bidding down attack aims to degrade or disable the security mechanisms within the current network. You can imagine a remote attacker disabling your car safety systems. So, how can we approach assessing the security of all these mitigations? We started with an analysis of the specifications and focus on the paragraphs and content which deals with the bidding down and security related paragraphs. Then we use that analysis to develop multiple test cases. With these test cases, we actually test the implementation of phones and network equipment. For testing, we mainly use SAS Run and Open 5Gs. The testing was done in our shielded laboratory in the university as well as in the test laboratories of the operator networks. We then take our results from our testing and try to forge different types of bidding down attacks. Now coming to the more interesting part, the test results. We have here two tables in which some latest flagship phones are included, such as the Samsung S22, as well as on the top side open source core networks as well as commercial core network equipment. Each black dot you can see means actually that a specific test target failed a security test. And as you may have noticed, there's a lot of black dots. So now, what we want to do is combine these findings to forge different types of bidding down attacks. Before I get to the first attack, I want to quickly recap some characteristics of a 5G non-standalone network. In a 5G non-standalone network, the UE is connected to a 5G GNOT-B, usually for user data transport, as well as to a concurrent LTE base station, where also signaling is included, which is in return connected to an LTE core network. Note that there are many non-standalone deployment options And this option 3 is, as far as I saw, the most deployed. When a phone connects to an LTE network, it has to indicate which security algorithms it actually supports. In a 5G non-standalone network, the UE has to actually manage two capability sets, one for the connection with the LTE, and one, the 5G NR algorithms, to activate security on the radio connection with the G Node B. These 5G non-standalone capabilities are called UE additional security capability and play an important role in the following attack. So the first attack I want to present is a 5G non-standalone NER null bidding down attack. The goal of this is to manipulate the 5G non-standalone security capabilities to disable encryption with the G Node B. This requires injecting a single NAS message, which is the initial NAS message, where also the security capabilities are included. Researchers from the ETH Zurich have demonstrated that this is practically possible. Now, coming to the actual attack, the call for is quite complicated, so I marked like 3 important parts that I'm going to talk about today. In the red box marked as 1, we can see that the attacker manipulated the attach or tau request where the 5G non-standalone security capabilities are included. The attacker basically sets all indication to false except for any NEA 0, which means basically don't use any encryption. And now we're coming also to the first specification flaw. In LTE, the core network, it is specified that the core network has to reject invalid security capabilities. And the capability set that only supports null encryption is classified as invalid. However, for the 5G non-standalone security capabilities, there's a blind spot in the specification. This means that the core network accepts these manipulated and invalid capabilities. In the second step, in the blue box, we can see that the core network then sends a NAS security mode command message. This message includes 2 information elements that are of interest for us today. The first one being the replayed UE additional security capabilities. Here, the core network includes the capabilities it received initially unprotected and includes it in the integrity protected NAS security mode command message. This allows the UE to verify whether an attacker tampered with these capabilities. The second interesting information element is the hash MME. The core network actually calculates a hash of the initial NAS message and includes it as well in the NAS security mode command. This means that the NAS security mode command actually provides 2 security mechanisms to detect manipulated 5G NSA security capabilities. However, we have found 2 major phone vendors that did not implement these checks correctly. The result of this is that both the UE and the core network now trust these tempered security capabilities. And in step 3, you can see that the network eventually then activates null encryption on the radio connection with the G Node B. The second attack I want to talk about is a 5G downgrade dance. The goal of this attack is to basically downgrade a UE from 5G down to 2G. For this, an attacker has to operate at least 1 fake base station for 5G and 4G. In the real world, this requires sophisticated hardware and is not very easy to implement. The attack goes as follows. The attacker lures the UE into connecting with his 5G fake base station. The UE sends a NAS registration request, and the fake 5G network immediately responds with a NAS registration request with the specific cause 27 and 1 mode not allowed. This reject cause forces the UE to disable its 5G capabilities completely for the given PLMN. What the phones now do is they immediately search for available cells in the next lower generation. This is then 4G. Then if the attacker manages to lure the UE into the fake 4G base station, he repeats this process. The phone sends an LTE NAS attach request, and the fake 4G network immediately responds with a NAS attach reject with the specific cause, severe network failure. In the past, research have demonstrated different reject causes that could downgrade a UE from 4G. We have tested those as well, and the result was that they do not work reliably on the latest flagship phones anymore. That's why we wanted to introduce this new reject cause severe network failure, which worked on all phones we have tested. The result now is that the only option left is to search for a 2G connection and attach to a 2G network. As we all know, 2G provides no effective security mechanisms. So there are two reasons why I did skip 3G here. The first one being that in Europe, 3G is almost completely deprecated, while 2G is still alive because of legacy compatibility. The next reason is that an attacker actually can do a redirection attack from 4G to 2G. This means that the fake 4G base station can tell the UE, do not attach in 4G, go directly to that 2G cell at that given frequency. This attack was also published many, many years ago, and the 3GPP actually implemented security features to prevent unauthenticated redirection attacks. We have tested all operators and none of them actually implemented this. And even if they did implement this, we have found multiple major phone vendors that failed to implement it on the UE side. The last attack I want to present is an identity bidding down attack. In 5G, the SUCI replaces the IMSI to protect, for example, against IMSI catchers. Attackers can bypass the SUCI protection if the UE exposes its IMEI to an unauthenticated identity request. The attack is actually pretty simple. The attacker has a fake 5G base station and lures the UE into connecting. After the registration request, the attacker sends an unauthenticated identity request, but does not request the identity type SUCI, but sets it as IMEI. Again, we have found two major phone vendors who did not implement a secure check, and these phones exposed their identity, their IMEI in an unprotected identity response. Catching the IMEI is actually more devastating than the IMSI, because it is more likely that you're going to swap your SIM instead of swapping your phone. With that, coming to my conclusion. Bidding down attacks remain a problem due to implementation errors and incomplete specification. We are collaborating with the GSMA to propose specification improvements to the 3GPP. These are currently discussed in the 3GPP. We responsibly disclose our findings to vendors such as Samsung, Google, Qualcomm, Huawei, and Unisoc. We got some CVEs assigned, but even more bugs got fixed. But some companies decided to simply sometimes not attach any CVE at all, or don't do it for issues that are graded as lower or medium security problems. More info can be found on our web page, 5G Downgrade. That's it from my side, and I thank you for listening.
Thanks a lot. Do we have time for a couple of questions? Are there any questions? Please. Yes.
All of these attacks can be detected at the UE. Right? The UE can detect these attacks. Right?
Yes, if it's implemented correctly, then the UE can detect it.
Right. And I think they should be. And for example, Samsung already detect downgrading. You can disable downgrading to 2G. Right?
I know for the Pixel phones, they implemented disallowing 2G.
And because we don't know how the carrier is going to set or weaken their security settings, right? So I think I don't know how widespread or how those phone vendors are some of these.
I mean, at least, for example, the security capabilities, these security mechanisms are already implemented in the specification, should be mandatory. But as we can see, some just don't do it, miss it, and then we have the implementation for us that can be abused. But of course, if it's an implementation error, it cannot be exploited very widespread. It has to be that baseband model, and it requires some effort to do it actually in real world.
Thank you for the talk. I was wondering, would you be able to go to slide 11? I had a question on that.
Of course.
So this second message of the replayed UE additional capabilities, right? This is exactly there to see whether in flight somebody changes this, right?
Exactly.
Now, are you saying this is an implementation error on the core side or the device side?
On the device side, because it has to check it,
Right.
and if they're invalid, he has to reject the security mode.
Right, yeah, but so there are phones that do not do this check.
Exactly.
So it's not a standard issue.
This is not instant. The first point isn't standard issue, which is that the core network shouldn't even accept these manipulated
right. Okay. So
capabilities because
you're
it's
saying
invalid.
that no encryption should not be considered a valid security configuration.
Exactly. And there's no, for the 5G non-standalone, there's no integrity protection, at least until release 15. It's now decided in release 16, but that's going to take some time until it's deployed, I guess.
Okay. Okay. Thank you very much.
You're welcome.
Last question?
So isn't non-encryption is optional? So no encryption is optional, right?
No,
It's not mandatory.
no encryption. Encryption is not mandatory,
Right.
but compared to the LT specification, it says that a capability set that only supports null encryption is invalid because it has to support at least one of the following three algorithms.
Okay, let's thank the speaker.
Thanks for listening.